Hi friends, today we discuss about the Thevenin theorem. Thevenin's theorem which simplifies complex electrical circuits. Hermann von Helmholtz, a German physicist, first demonstrated the theorem in 1853. His work focused on the electromotive properties of conductors, including animal tissue. However, Leon Charles Thevenin, a French telegraph engineer, independently developed a more elegant method for proving the theorem in 1883. His proof was closer to modern electrical engineering practices. Thevenin's name is more commonly associated with the theorem due to his more streamlined approach to circuit analysis. While Helmholtz's work predates Thevenin's more accessible approach to circuit analysis made the theorem widely known and is the reason why it's commonly named Thevenin's theorem. First of all, we know about the statement of Thevenin's theorem. Thevenin's theorem states that a linear network consisting of a number of voltage sources and resistances can be replaced by an equivalent network having a single voltage source called Thevenin's voltage V underscore TH and a single resistance called Thevenin's resistance R underscore TH. This simplification allows for easier analysis of the circuit's behavior at specific terminals, where Thevenin's voltage means this represents the open circuit voltage across the two terminals of the complex network. It's the voltage that would be measured if no load were connected across those terminals. It indicates the VTH or V underscore TH. Next, Thevenin's resistance means this represents the equivalent resistance of the network when viewed from those two terminals, with all independent voltage sources replaced by short circuits and all independent current sources replaced by open circuits. It indicates the RTH or R underscore TH. Next, we discuss about the explanation of the Thevenin's theorem. Let E be the electromotive force of the cell having its internal resistance Ri equals to 0, where electromotive force is the energy provided by a power source like a battery or generator per unit charge to move electric charges through a circuit. Simply, EMF is the potential difference across the terminals of a source when no current is flowing. It is denoted by epsilon or EMF, measured in volts V, where internal resistance is the resistance within a power source like a battery or generator that opposes the flow of current. In simple terms, internal resistance reduces the terminal voltage of the cell when it's delivering current. It is denoted by Ri or R underscore I, measured in ohms. Let RL be the load resistance across AB, where load resistance, also known as load impedance, refers to the resistance offered by a device or circuit that consumes power from a source. In simple terms, load resistance is the resistance of the external component or circuit that is connected to a power source and consumes electrical energy. It is denoted by RL or R underscore L, measured in ohms. Next, the image shown a schematic diagram of an electrical circuit containing a voltage source E and four resistors R1, R2, R3 and RL connected between points A and B. Resistors R1 and R3 are in series and their combination is in parallel with R2. Resistor RL is in series with the combination of R1, R3 and R2. Series configuration means the equivalent resistance of resistors in series is the sum of their individual resistance, means same current flowing through them. The formula for calculating total resistance that equals to R1 plus R2 plus R3 and so on Rn, where R1, R2, R3, R4 represents the resistance of individual components. Parallel configuration means resistors connected in parallel have the same voltage across them and their total resistance is calculating using the formula 1 by R1 plus 1 by R2 plus 1 by R3 and so on 1 by Rn, where R1, R2, R3 represents the resistance of individual components. Next, we find out the value of Thevenin's voltage, means VTH or V underscore TH. The load resistance RL is removed. Simply, the load resistance is disconnected from the terminals A and B. Already, we know load resistance refers to the opposition that a load offers to the flow of electric current in a circuit. The circuit diagram depicts a combination of resistors connected to a voltage source. To analyze this circuit, it's important to understand how to calculate the equivalent resistance and apply circuit laws. A circuit with voltage source E, resistors R1, R2, R3 and a load resistance RL is considered. To find out the Thevenin's voltage, to remove the load resistor. In this case, the load is considered to be between points A and B. The current I in the circuit is calculated using the formula I equals to E by R1 plus R2. This is the equation number 1, where E is the voltage source. R1 and R2 are the resistances in the circuit. The voltage across AB, that equals to Thevenin's voltage VTH. It means in the circuit diagram, the voltage across terminals AB is indeed equals to Thevenin's voltage, which is also known as the open circuit voltage across those terminals. The Thevenin's voltage represents the voltage provided by the equivalent circuit. That Thevenin's theorem simplifies a complex circuits also. VTH equals to IR2. This is the equation number 2. Here, VTH equals to IR2 represents a formula related to Ohm's law. Already, we know about the Ohm's law. This law states that the voltage V across a resistor is directly proportional to the current I flowing through it and the resistance R of the resistor. Mathematically, it's expressed as V equals to IR. Therefore, VTH equals to IR2 could be represent the Thevenin voltage being calculated using Ohm's law, where I is the current and R2 is a specific resistance in the circuit. From 1 and 2 equations, current I value substitute on the equation number 2. We get VTH equals to I, means E by R1 plus R2 into R2. Finally, VTH equals to ER2 by R1 plus R2. This is the equation number 3. This equation represents the Thevenin's voltage in a circuit. This formula is derived from the voltage divider rule. The voltage divider rule is a way to calculate the voltage drop across a specific resistor in a series circuit. It's based on the principle that the voltage across a resistor is proportional to its resistance in the series circuit, where E is the source voltage, R1, R2 are the resistors in series. VTH is the voltage across resistor R2, simply Thevenin's voltage. Next, we find out the value of Thevenin's resistance, means RTH. This image shows a resistive circuit used to find the Thevenin equivalent resistance between the terminals A and B, where R1, R2 and R3 are resistors. R1 is in series with R2. The combination of R1 and R2 is in parallel with R3. The entire configuration lies between terminals A and B. The goal is to find the Thevenin's equivalent resistance as seen from points A and B. The load resistance RL is removed. Simply, the load resistance is disconnected from the terminals A and B. The cell is disconnected and the wires are short as shown in figure. It means to calculate Thevenin's resistance, you replace all independent voltage sources with short circuits and all independent current sources with open circuits. Then calculate the resistance between terminals A and B. Simply, the effective resistance across terminals A, B with the cell disconnected and wires shorted is known as the Thevenin's resistance. The effective resistance across AB that equals to Thevenin's resistance. It means the effective resistance across any two terminals AB is indeed equal to Thevenin's resistance when Thevenin's theorem is applied to simplify the circuit. Thevenin's resistance RTH equals to R3 plus R1 R2 by R1 plus R2. This is the equation number 4. R1 is the parallel to R2 and this combination in series with R3. In simple words, the current flows through R1 and R2 separately, then the combined current flows through R3. If the cell has internal resistance Ri, the Thevenin's voltage and Thevenin's resistance formulas are given below. From equation 1, we write Thevenin's voltage VTH equals to ER2 by R1 plus R2 plus Ri, where E represents the voltage source. R2 is a specific resistance in the circuit. Ri and R1 are other resistance in the circuits. The formula represents the output voltage across R2, which is derived from applying the voltage divider rule to three resistors in series Ri, R1 and R2. It tells you how much of the source voltage E appears across R2 considering all series resistance. From equation 4, we write Thevenin's resistance in a circuit RTH equals to R3 plus R1 plus Ri into R2 by R1 plus R2 plus Ri, where R1 and Ri are in series. R2 is connected such that the combination of R1 plus Ri is in parallel with R2. R3 is in series with the whole parallel network. Next, we discuss about the proof of Thevenin's theorem. The circuit 1 appears to be a Thevenin's equivalent circuit analysis setup involving a voltage source, several resistors and load resistor, where E represents voltage source, R1 represents resistor in series with the voltage source, R2 resistor connected from the node between R1 and R3 to ground forms a voltage divider. R3 represents resistor in series with the output or load section. RL represents load resistor connected between terminals A and B. I1 and I1 currents through different branches. A and B are terminals where we might want to find the Thevenin's equivalent. This is circuit 2, which represents the Thevenin's equivalent circuit, where VTH represents the Thevenin's equivalent voltage, means the open circuit voltage measured across terminals A and B on the original circuit. RTH represents the Thevenin equivalence resistance, means the resistance seen from terminals A and B when the independent voltage source in the original circuit is turned off, replaced by a short circuit. RL represents the load resistor connected across terminals A and B. I2 represents the current flowing through the loop, means same current through RTH and RL. Already we discussed, consider the network as shown in circuit 1. The equivalent Thevenin circuits as shown in circuit 2. The effective resistance of the network in circuit 1 is R3 and RL in series, and this combination is parallel to R2, which in turn is in series with R1. We write effective resistance formula is the effective resistance that equals to R1 plus R2 into R3 plus RL by R2 plus R3 plus RL. R3 and RL are in series, so their combined resistance that equals to R3 plus RL. This series combination is in parallel with R2. So, the parallel combination becomes R parallel that equals to R2 into R3 plus RL by R2 plus R3 plus RL. This result is in series with R1. So, the total effective resistance is finally effective resistance that equals to R1 plus R2 into R3 plus RL by R2 plus R3 plus RL. This is the equation number 1. The formula for the current driven in the circuit is I equals to E by effective resistance, where I is the current, E is the voltage, R underscore EFF is effective resistance. We know the amount of current available from such a source is given by the ratio of the voltage across the voltage source to the resistance of the resistor. Already we know the Ohm's law, E equals to IR. It is a fundamental principle in electronics stating the voltage E across a circuit element is equals to the current I flowing through it multiplied by the resistance R of the element. So, the formula of current I equals to E by R. E represents voltage measured in volts V. I represents current measured in amperes. R represents resistance measured in ohms. This relationship allows to calculate any of the three variables E, I, or R if the other two are known. Finally, I equals to E by effective resistance. This is the equation number 2. From 1 and 2, the effective resistance value substitute in the equation number 2. So, I equals to E by R1 plus R2 into R3 plus RL by R2 plus R3 plus RL. The numerator E didn't any change. We take denominator. The above equation we take LCM. Here the denominator value 1 into R2 plus R3 plus RL, that equals to R2 plus R3 plus RL. Next step, R1 into R2 plus R3 plus RL, that is R1 into R2 plus R3 plus RL. And next the denominator R2 plus R3 plus RL and R2 plus R3 plus RL are cancelled. So, remaining term, the numerator R2 into R3 plus RL. Finally, I equals to E by R1 into R2 plus R3 plus RL plus R2 into R3 plus RL whole by R2 plus R3 plus RL. Next, the denominator R2 plus R3 plus RL, that is converts the numerator, means E into R2 plus R3 plus RL. Finally, I equals to E into R2 plus R3 plus RL by R1 into R2 plus R3 plus RL plus R2 into R3 plus RL. This is the equation number 3. The current through the load resistance I1 is found using branch current method. The branch current method is a circuit analysis technique that determines the current in each branch of a circuit by assigning currents to each branch, applying current and voltage laws, and solving the resulting equations. This method is a fundamental approach to analyzing DC networks. The current through the load resistance I1 equals to IR2 by R2 plus R3 plus RL. This is the equation number 4. The formula shown in the represents a way to calculate current division in a parallel circuit. Specifically, it calculates the current I1 flowing through resistor RL in a circuit with multiple parallel resistors, where I1 is the current flowing through resistor R2. I is the total current entering the parallel section of the circuit. R2 is the resistance of the resistor where the current I1 is being calculated. R3 is the resistance of another resistors in parallel with R2. R1 represents the load resistance, which is the total resistance of the rest of the circuit. From 3 and 4, current I value substitute in the equation number 4. We get I1 equals to E into R2 plus R3 plus RL into R2 whole by R2 plus R3 plus RL into R1 R2 plus R1 R3 plus R1 RL plus R2 R3 plus R2 RL. Above equation, the numerator R2 plus R3 plus RL and the denominator R2 plus R3 plus RL are cancelled. We get I1 equals to ER2 by R1 R2 plus R1 R3 plus R1 RL plus R2 R3 plus R2 RL. This is the equation number 5. We know equations 3 and 4. Again, we write Thevenin's voltage VTH equals to ER2 by R1 plus R2. This is the equation number 6. Next, Thevenin's resistance RTH equals to R3 plus R1 R2 by R1 plus R2. This is the equation number 7. Consider the equivalent circuit in figure 2. Already we discussed about the circuit diagram 2. The current I2 in the equivalent circuit is I2 equals to VTH by RTH plus RL. This is the equation number 8, where I2 represents the flowing current. VTH is the Thevenin's voltage, which is the open circuit voltage across the terminals of the original circuit. RTH is the Thevenin resistance, which is the equivalent resistance of the original circuit, looking back from the terminals with all independent sources turned off. RL is the load resistance connected across the terminals. This formula is derived from Ohm's law. We know Ohm's law V equals to IR. So, I equals to V by R. From 6, 7 and 8 equations, Thevenin's voltage VTH and Thevenin's resistance RTH values are substituted in the equation number 8. We get I2 equals to ER2 by R1 plus R2 by R3 plus R1 R2 by R1 plus R2 plus RL. Next step, inverting and multiplying the divisor. I2 equals to ER2 by R1 plus R2 into 1 by R3 plus R1 R2 by R1 plus R2 plus RL. Now, the division becomes multiplication with the reciprocal of the denominator. Next step, combine the terms under a common denominator. I2 equals to ER2 by R1 plus R2 into 1 by R3 into R1 plus R2 plus R1 R2 plus RL into R1 plus R2 by R1 plus R2. Bringing everything to a single denominator for simplification. The above equation multiplied by the numerator and denominator terms. So, we get I2 equals to ER2 by R1 plus R2. R3 into R1 plus R2 plus R1 R2 plus RL into R1 plus R2 by R1 plus R2. Expand the terms. R3 into R1 plus R2, that equals to R3 R1 plus R3 R2, and RL into R1 plus R2, that equals to RL R1 plus RL R2. We write the above equation. I2 equals to ER2 by R1 plus R2, R3 R1 plus R3 R2 plus R1 R2 plus R1 RL plus R2 RL by R1 plus R2. Here R1 plus R2 and R1 plus R2 cancelled. Finally, I2 equals to ER2 by R3 R1 plus R3 R2 plus R1 R2 plus R1 RL plus R2 RL. This is the equation number 9. This is a simplified and expanded expression for the branch current I2. From equation 5 and 9, it is observed that two equations are equal. That is, I1 equals to I2. This is the equation number 10. The relationship between the current in the simplified circuit I1 and the original circuit's load current I2 is that I1 equals to I2 if I2 is the current in the load resistor of the equivalent circuit. Finally, Thevenin's theorem is verified. This is our brief explanation of the Thevenin's theorem. Thank you very much. Padmam Himam.